Okay, picture this. You're sitting in your IGCSE computer science exam. You read a question, you confidently scribble down your answer, and you move on, feeling pretty good about it. But here's the thing, 9 out of 10 students make a massive mistake right off the bat, and it quietly bleeds away their grades. Seriously, it happens all the time. Let me show you exactly what this error is before you make it yourself. Welcome to today's explainer, where we're going to reverse engineer the examiner's mark scheme and absolutely lock in your understanding. So say you write something like what we have here. It checks the data to make sure it's right. I mean, it seems completely logical, doesn't it? Well, actually, scratch that. That gets you exactly 0 marks. None. Why? Because this is a classic textbook cold open mistake. It's way too vague, it's super generic, and it uses everyday language instead of precise computer science terminology. This is the trap. The examiner doesn't want to know if you just kind of vaguely get the vibe of the idea. They want to see if you can execute the exact technical logic. Now, what's really fascinating here is looking at common student errors right alongside the exam-ready fixes. Vague wording? That gets you nothing. Naming a process without actually explaining how it works also gets you nothing. Like, if a question asks about robotics in a factory and you give some generic answer about computers in general, you lose the mark. You absolutely must anchor your explanation to the specific details provided in the prompt. We call these your scenario nouns, and they are your best friends. All right, moving into section 1, the examiner's favorite trap, because vocabulary absolutely matters. Here's the hard truth. Knowing the underlying concept is literally just the starting line. The examiner's favorite trap is letting you talk yourself out of a mark simply because you didn't use the required structural vocabulary. It isn't just about what you know, it's about exactly how you write it down. To secure those high marks, you need a really disciplined 4-step structure. First up, you provide the definition. Second, you explain the mechanism, like how it actually works step by step. Third, provide a scenario example using those exact nouns from the question prompt. And finally, use precise examiner wording. So instead of writing "it checks the data," you write "a range check ensures the input value is between the predefined limits." Boom, that is how you win the mark. Okay, section 2, software and system foundations. Or as I like to think of it, translating human thought to hardware. Let's dive in and see how human thought actually translates to hardware execution using specific scenario nouns. Because before we can even think about fixing our code, we need to understand the environment it lives in. Think about it for a second. We sit down, we type readable words on a keyboard, and suddenly a physical machine made of silicone and metal actually does something in response. It's kind of wild. But what exactly bridges human desire to physical hardware action? Think of software as a literal physical bridge. On one side, we have human thought and high-level human-readable languages, things like Python or Java. But the hardware execution on the far side, it only understands machine code, just raw ones and zeros. To get across this bridge, our high-level code has to pass through a language gap using translators. Specifically, we're talking about compilers which translate the whole program all at once, or interpreters which translate it line by line. So the whole process flows in 3 very distinct steps. You've got high-level human code, then translation via a compiler or interpreter, and finally, binary hardware execution. But notice the massive structure supporting this entire bridge? That's the operating system. The OS acts as the ultimate manager orchestrating this whole shebang. It handles the hardware, runs the application software, and manages any interrupts that pop up. Let's keep moving. Section 3, Mastering Algorithms and Logic, Choosing the Right Path. You know what's really interesting about logic? Just one single poor choice in your pseudocode can literally derail an entire algorithm. I mean, you can have the perfect hardware and the perfect translator, but if your logical instructions are messy, the machine executes a mess. So let's focus on the 2 required pillars of selection. In pseudocode, we have if statements, which act as a linear logic gate, moving step by step through true or false conditions. And then we have case statements, which give you this clean, multi-way branch based on specific values. A massive trap students fall into is just spamming nested if statements for everything, which makes their algorithms incredibly hard to read. And this right here is the exact exam upgrade you need. If then else is perfect when you are dealing with ranges or complex logic, like, say, checking if a test score is greater than 50. But case of otherwise, it's purpose-built for multiple specific discrete values, like checking if a chosen color is specifically red, blue, or green. In an exam, if you're asked why case is better, you must explicitly state that it is more efficient and easier to read when dealing with specific, discrete choices. Section 4, the fetch, decode, execute cycle, the absolute core of CPU processing. Let's pivot to the physical hardware and see how this builds the absolute core of computer science. How does the CPU actually process these logic gates we just wrote? Look at the disciplined exam method for the fetch, decode, execute cycle. Notice how it demands total specificity over abstraction. The exam requires you to systematically identify the demand, classify the concept, explain the mechanical sequence, and then connect it all back to the specific context provided, whether that's an office network or a school system. The contrast here is huge. It's everyday language versus technical vocabulary. You have to separate the name of the process from the explanation of how it actually works. Don't just say it fetches the data. You need to explain that the CPU fetches the instruction from memory, decodes it into a format the arithmetic logic unit can process, and then executes it. Name the specific components. All right, Section 5, validation, input, and storage, checking the rules. So a crucial point here is making sure the data our CPU processes is actually reasonable and correctly stored before it is executed or transmitted. Because if bad data goes in, bad data comes out, no matter how fast your processor is, right? Let's do a rapid-fire challenge to test your retrieval right now. If an exam question asks you to test the rule, number must be strictly less than 100, what specific data type is the number 99? Is it normal, extreme, abnormal, or boundary? Think about it for a second. If you said boundary data, you absolutely nailed it. The boundary data rule makes this super clear. 99 is exactly on the edge of the accepted range, making it accepted boundary data. 100 is immediately outside the accepted limit, making it rejected boundary data. Testing the very edge of your logic is exactly what examiners are looking for. Now, whatever you do, make sure you never, ever mix these two terms up again. Validation asks, is the data reasonable and possible according to the rules, like ensuring an age is actually entered as a number? Verification, on the other hand, asks, does the data match the original source, like entering a new password twice just to ensure it was typed correctly? Remember, validation cannot prove data is perfectly correct. It only proves that the data is permitted to enter the system. And finally, Section 6, Final Exam Ready Recap, your blueprint for success. Let's lock in everything we've covered today. We are looking at a final exam-focused strategy that applies across all these syllabus topics, whether you're tackling hardware, software translation, or pseudocode logic. Here is your blueprint for elite answers. 1. Strictly no generic phrasing. 2. Always define the term and then explicitly explain the mechanism of how it works. 3. Anchor your answer to the scenario nouns provided in the question. And 4. Know exactly how to test your logic using normal, abnormal, and boundary data. Applying these steps literally transforms a weak, zero-mark guess into a perfectly safe, mark scheme-approved response. So I'm going to leave you with one final provocative challenge to test your new skills. Based on everything we explored today, can you define the mechanism of packet switching right now using this exact high-mark structure? Think about the definition, the step-by-step mechanism, a real-world scenario, and the precise terminology. Master that, and you won't just memorize the syllabus. You will truly command it. Thanks for learning with me on this explainer, and I'll see you in the next one.